Okay, assalamualaikum and good morning. So, let me introduce myself first. So, I'm Dr. Hishamuddin. Okay, you can call me Dr. Hisham. And I'll be teaching this particular course, PHY3602 on Statistical Mechanics. I believe everyone has taken up modern physics or thermodynamics. Please say yes or no. Okay, great. So in other words, the first few lectures are probably going to be some revision to you, okay, and until we get to the more advanced section. So let me just mention the book that I'm going to use. The book I'm going to use is essentially, maybe I'll show the book cover first. You probably have seen this in the icon for the WhatsApp group. Okay, where is it? Can you see the screen? Great. So this is the book that I'm going to use. Okay. Essentially, from my survey of this of books on statistical mechanics, this is probably the easiest. So I recommend you to buy it if possible. But you can also try to look it up on the web. Okay. So and the other book, probably this was also recommended by reviewers of this particular book. Okay. That it should be read together with this other book by Cromer and Kittel, which is on thermal physics. This I will use just an additional thing if there are things which are not really covered by Bauli and Sanchez, which is the book earlier. I will try to look it up in Kittel and Cromer. But there are many other books, many other good books by on statistical mechanics. Let me just mention a few. So let me go to the whiteboard. Can you see the whiteboard? Okay. Hopefully this works. Okay, great. So there are other books like Landsberg, which is pretty old as well. Most of the books are quite old, and the modern books are much more advanced. So that's why we tend to use the old books. So this is thermodynamics and statistical mechanics. Yeah. Enter the room. Okay. I've done some auto admit. Okay, all right. So there are about nearly 40 of you. Huh? Okay, that's going to be a big class. Where was I? The whiteboard. Okay, so these are another book which is a standard book. Another one is Gerson Huang. Okay, which I think is like Intro to Stat Mechanics. And of course there are many more. Okay, you can just many others. Okay, so these are essentially if you find trouble for a particular topic, you just have to scout around to see how other books treat that particular topic. So I think that's the best I can advise you. But I will try to follow closely this book by Bowley and Sanchez. So this is the book that I'll be using. I will mainly on this particular book until I find something which is to add beyond this book. Okay. Right. What else I should be saying? Oh yes. The book by Cromer is actually a Nobel laureate. Yes, you can read about Herbert Cromer over here. Okay. He wins the Nobel Prize. He's doing all this semiconductor device. So read up some history. The main father of what you call statistical mechanics is Boltzmann. You probably have heard about Boltzmann constant before, but Boltzmann is the one who drives statistical mechanics to a much modern what you call, framework beyond thermodynamics. But there's a nice piece of history behind this. Initially, Boltzmann's idea was not accepted among the physicists. So in the end, he committed suicide. But no, that's him. Okay, yeah, we should learn to be more striveful, more patient with statistical mechanics. And many of these ideas are already being established. So in other words, the things that we're going to learn are pretty much accepted now. Okay. I used to, in the last 2 semesters, I used a different book which begins with Boltzmann equation, but Boltzmann equation is pretty tough to understand, so I'm using an easier book this time. Okay. So, right. The other thing that I'm going to say is about the assessment plan. So the assessment plan is shown over here. There will be test 1 and test 2 as usual. This will take up about 15% each. Okay, this is should be around week 4 to 5. Depend on the situation. Usually week 5 is a bit busy with the other tests as well. And then test 2 will be in week 10. Okay, again 15%. So that covers up 30%. There should be, okay, the final exam of course is 40%. There should be another 70%, another 30%, okay? So this is 70%. The other 30% is coming from assignments, 10%. Quizzes, again, having online quizzes are not my real favorite, but no, okay, we can have some online quizzes randomly towards during the weeks of the semester. And then we will have sometime before the semester break, I'll give you an SCL, student-centered learning modules, okay, where you have to review certain papers in a group, okay. So that is about 15% there. So this sort of more or less, when you review these papers, it gives you some ideas about what is still interesting in research among the topics of statistical mechanics. Okay, and then there will be, of course, the final exam. Okay, so that makes up 100%. So are there any questions about this? Please, I cannot see you while I'm on this screen mode. Are there any questions with respect to this assessment plan? Okay, good. Right, so now I suppose we can start our lectures now. So this will be the first lecture. which is again, I just mentioned this as coming straight from the book, but I try to summarize it a little bit and add a few extra facts. This is on the preliminaries of before you even learn about statistical mechanics. We have to look at topics of thermodynamics beforehand in order for us to get to the point of understanding statistical mechanics. So if you how I can do this, let me just check. Okay, so thermodynamics are essentially an empirical subject. Okay, can you see the red what you call circle there? Okay, great. Okay, so do you know what empirical means? Anyone? What does an empirical what you call topic means? You have to let me know if there are words I use which is not properly understood, then let me know. Okay, in this case, empirical means it derives from, oops, it derives from experiments. Okay, so some of the things are not from some postulates, but these are just observations of experiments, and normally it's when you do thermodynamics, it's actually framed in with respect to what we call energies. Okay, so when you do thermodynamics, you recognize heat, for example, as an energy, and work done. Essentially, if you understand mechanics pretty well, work done is just something which is realized from some potential energy and converted to some kinetic energy. Okay, so I think it was called kinetic work theorem or something like that. Okay, and then the other part of thermodynamics that you should understand, it always discuss about macroscopic concepts or variables. So these are variables which are known to describe the system as one big system. Okay, so the main idea of statistical mechanics is actually to be able to derive thermodynamics from a much more what I call a microscopic point of view. Okay, so this is a microscopic point of view, and if according to Boltzmann, okay, according to Boltzmann, he uses this idea of atomic hypothesis in some sense. Okay, so in those days when Boltzmann's ideas was not really accepted, they were against this idea of putting what I call some fictitious ideas of atoms to describe what they see in physical systems. So everything was actually phrased in terms of energies. So there's a school of statistical mechanics in some sense, or thermodynamics for that matter. They are just framing everything in terms of energies. Okay, so they are very much against the atomic hypothesis of Boltzmann. But here is where you get much more, when you do microscopic view, you have a stronger what I call explanatory power. Explanatory power. Okay. You actually tell how the microscopic particles actually behave, and collectively they will appear to give you all this macroscopic kind of behavior. Okay, so in our context, we talk about system. Systems are the things that we are going to be studying, and they will consist essentially of a large number of particles, okay, or the atoms, okay, and they are normally contained in some vessel, and this vessel could actually interact with the surroundings, okay? And how this the interaction happens depends on the nature of the wall of the vessel itself. So a complete isolated system or a thermally isolated system, the walls of the vessel will be what we call the adiabatic wall. Okay, so this is essentially an ideal insulating wall. But these are, as I said, is an ideal case. Normally, walls do have some form of, it allows leakage of heat and things like that. So there, in realistic cases, we are talking about diathermal walls. So what happens in this particular case, we consider these systems, and then over time they may have what we call interactions with the surroundings, okay, and then they go to some equilibrium state together with the surroundings, okay. So what is equilibrium is the state of the system for which the properties do not change. We'll talk about this a little bit more later, okay. And when the properties do not change after some time, okay, then we say that the system is in a state of equilibrium, okay. So one of the importance of having an equilibrium state is that you'll be able to describe them according to this macroscopic behaviors or macroscopic variables. And for instance, the one that you have probably have seen is the case of pure gas in equilibrium, okay, where you specify the state of your pure gas in equilibrium by the volume, pressure, and the number of particles. Okay? So these are variables that define the state of the pure gas. Okay? So an example is probably you can think of a cylinder of gas, okay, and then you have a piston which is movable, okay, just like your syringe, okay, and you allow this either the piston to move in response to pressure. For example, you can put some weights here. Okay, I'm having a problem with this. Can put some weights over here, so you increase the pressure, and then this piston goes down and the volume gets smaller, and when the volume gets smaller, the particles inside here gets heated, and then the temperature change, okay, things like that. So it can also be immersed in some environment for which there are heat, okay. So then this will get what you call thermally excited, and then it starts to exert pressure, and then the piston goes up, okay. So these are cases where you can consider the piston of gas inside that cylinder, the cylinder of gas with the piston, okay, which is considered as a system, and then the surroundings are just the environment, okay. The other thing that one should also know is, okay, once the system doesn't change with respect to its properties, that means what happens in that particular case, it is in equilibrium with the surroundings. Now one could actually do a much more refined experiment. So you consider two thermally isolated systems, okay? So individually they are they are isolated. There's no exchange of heat, but then you can put them together, and when you put them together, you remove the adiabatic walls, okay, and then you replace it by a common diathermal wall. So in other words, you have a two system here. So these are all adiabatic wall, and the wall that separates system 1 and system 2 is a diathermal wall. So in that particular case, there will be energy exchange between system 1 and system 2. Okay. So in other words, initially it will not be in equilibrium with each other. So, but once the energy starts to flow between system 1 and system 2 or back, okay, then they start to exchange energies until they come to a certain point where there's no net flow of energies between the two systems. Okay, so then we say that these are actually arriving to a new state of equilibrium of the two systems as a composite system. Now one could ask, can the new equilibrium state to be the same as the initial states of the two systems? Well, it can only be in the case when the two systems are already in equilibrium with each other. Okay, otherwise there will always be a net flow of energy. Okay, and this idea becomes the basis of the Zeroth Law of Thermodynamics. Okay, so if one system, say one system A is in equilibrium with another system C, and then B is also another system which is in equilibrium with system C, then one can easily say that system A and system B are also in equilibrium with each other. So this is essentially the Zeroth Law of thermodynamics. Concept-wise, this is like transitivity. Okay, so this is like transitivity. Getting to the end of my cursor. Oops, what happens? Oh. Okay, it's back. So this is just like the concept of transitivity. So right, what else? And the Zeroth Law is actually forms the basis of the idea of the concept of the thermometer. So the thermometer is a device that tells us how the properties of a system changes with respect to time. So if you put a thermometer, for example, inside a system, then we start to exchange energy with the system, and then it will tell us, okay, once the energy sort of what you call energy flow sort of stops. How should I say? The net flow has already stopped. Then you'll be able to define what the temperature of this system is, because the thermometer is already in equilibrium with that system. Okay, so in other words, the thermometer is a device like the system C that we had in the Zeroth Law. Okay, so you can consider C in system A, so it's in equilibrium, so that means A and C is doesn't change properties anymore. And then you do the same for system B, then essentially that says A and B are in equilibrium with each other. Okay, so this is how one sees it. Okay, if you think of system C being the thermometer now, okay, you put together with system A and they are in equilibrium, so you don't see any change in the properties, so that means there's no change. The temperature has already been recorded to some extent. You have mentioned thermometer that usually is measuring temperature. Okay, and then you do the same for system B, then you find that there's no change in the properties of C. Then you expect when you put these two systems together, there will be no change of properties of either A or B. That means they are in the same, they are at the same temperature, so to speak. Right. Excuse me. Oh dear. No. Okay, saya tengah connect balik. Okay. Okay, can you see the notes now? Okay, I'm back. Can you see me now? Yes. Sorry, I think our Wi-Fi over here is not so good. Let me just share my screen again. This is the first time it happens. Please do give me a warning if this happens. Okay, so now where did I stop just now? Hello? Can somebody tell me where did I stop? When did I get disconnected? Okay, this one. Which one did I already start describing the thermometer? Okay. Okay, so I have to go back then. So in other words, when we have the zeroth law, it talks about how two systems are in equilibrium with the third, then essentially that tells us that the two systems are also in equilibrium with each other. So that helps to define what we call a thermometer. Okay, and the thermometer is like your system C in this particular case. So in other words, if it is in equilibrium with A and then it's in equilibrium with B, that means the thermometer was actually implies that A and B will have the same temperature, so to speak. Okay, so I will not go to too much description because I've done that during. You can read the notes if you. So the fact that in equilibrium, the idea is to see no change in the properties. Okay, so in other words, when the thermometer is in system A, then it records the temperature of system A. The fact that the thermometer is now already in equilibrium with A, so you will no longer see any change with respect to the properties of A anymore. Okay, and the same thing with B. And then if you put A and B together, then there will be no changes with respect to properties of A and B because they are at the same temperature, so to speak. So one can start to play around with a much more refined experiments, okay, where you do these systems at different pressures and volumes, and you have a reference system, for example, system A, and then you bring another system, system X, as a test system. Okay, so if system X when it goes into equilibrium with system A, then we say system X is isothermal with system A. Okay. So what we do in this particular case, one can start to talk about isotherms. So isotherms are what I call isotherms are essentially curves. If you draw the PV diagram in this particular case, the PV diagrams, then you find that okay, forms curves like this because, okay, maybe I should just mention about the ideal gas law first. PV equals constant. I think everyone knows about this since high school. So you can plot this type of curves, and you have this kind of sort of almost hyperbola type kind of curves. Okay, and essentially this constant over here is actually dependent on your temperature. If you remember, the ideal gas law would be PV nRT, right? Okay, so here I'm using theta as your temperature. So for every temperature, you have these curves of constant PV. Okay, so in other words, here by right I should not be talking about temperature as yet, but the fact that P and V is a thermodynamic variable behave in such a way that you obeys this PV equals constant, and then you can draw with respect to different P and different V, can draw a family of curves in this way. Okay, and then you can start to label each curve by the parameter that parameterize the curve. So in this case, your theta is like a parameter of the curve. Okay. So if you remember in maths method, when you write down a curve, that means there's a one-dimensional variable that runs through it. Okay, so in this particular case, it's like your theta runs through all this. Well, I mean, actually, it's the other way around. Okay, for each constant theta, then you have these curves of P and V. Okay, so this is what we call isotherms. Okay, if you think of what this iso means, and a term is actually thermal. Okay, so iso means the same, so that means it's the same temperature. Okay, so and between one curve to the next, for example, I can think of this as a neighboring curve. So you can think of going from this curve to this curve, that you can do it smoothly, you can change the curve smoothly. So in other words, the family of curves are parameterized by theta, but your theta sort of smoothly transits from each curve to the other curves. Okay. So then this is what we call the temperature. So I'm sort of taking the high school example to motivate this idea. But now you have the concept of temperature as one that arises from some thermodynamic variables, in this particular case P and V. Okay, so I can write your theta here, your temperature, as a function of P and V. Okay, and the instrument that reads of theta is called a thermometer. And initially, in those days, they have what we call a gas thermometer. But gas thermometer is a bit, it's not so accurate. Okay, so now there are they found a better temperature. In fact, the first accurate temperature thermometer, the first accurate thermometer was actually invented by Daniel Fahrenheit, circa 1700s, where it uses it's like the thermometer that you see nowadays. Okay, with a glass capillary tube, and then there's a bulb at the end containing mercury, and that is already good enough to give some accurate temperature measurements. Okay. What are the qualities for a good thermometer? So first of all, whatever properties that's going to measure it has to change significantly with the temperature. So in this particular case, if you think of the mercury bulb temperature, you can see that, okay, as you go to a hotter environment, the temperature goes up, and you can see the capillary of mercury going up inside the tube. Okay, and then it has to have a small heat capacity, so you have to understand what heat capacity is. We will treat this much later. Then a rapid approach to thermal equilibrium. So in other words, the thermometer has to be quickly be in equilibrium with the system that is trying to measure the temperature. Okay, and then it has to be reproduce well. Okay, if you have the same temperature, it should give you the same reading, and of course, if possible, it's applicable to a wide enough range of temperatures. Okay. Now, the mercury thermometer itself does not approach equilibrium rapidly. So that's why when you insert this mercury thermometer in a particular heated thing, it will, you can see that the capillary rise slowly. Okay, so it does not approach equilibrium rapidly, but this works quite well for large objects, because the large object, the mercury thermometer is trying to measure temperature, will not vary that much while it does that. Okay, so in other words, the mercury thermometer in those days are already good enough for ordinary things. Okay, these days, of course, you want to have a much more accurate temperature readings, then you need to be able to use some other kind of thermometers, like thermocouples and things like that. So there are other thermometers that are based on different properties like resistance, magnetic properties, things with respect to the stars. For example, they look at the radiation from the hot body. Okay? And then in some cases, color changes and so on and so forth. Okay, let me talk about equilibrium. There are three types of equilibrium considered in this case. Usually this is related to the kind of exchange of energies that you are allowed to have. Okay, So the first one is called thermal equilibrium. Okay, so these are telling you how the flow of energy between systems, and then these are recorded in terms of temperature. So when they are in thermal equilibrium, they will the system will be uh, uh, will correspond to the same temperature. Okay, and then you have your mechanical equilibrium. So this again like the piston thing. So you can put the piston inside a hot environment, then you can see the gas in the cylinder start to expand, and then the volume changes. Okay, so this is doing a mechanical work. Okay, so this is mechanical equilibrium, and then you can also have a chemical equilibrium. So the chemical equilibrium is mostly with respect to the type of particles involved in the interaction. Okay, so usually we think of some chemical reactions, for example, like this. You have a species C put together with species D, and they interact to give you a new species, bound systems CD, for example. Then you look at the number of particles of each species. Okay, at chemical equilibrium, then they will start to to stop changing this number of types of species. Okay, number of particles for each species. Okay, so an example is you put a electron and proton in plasma, for example. You can find hydrogen atoms forming on and off. Okay, just like in the sun, for example. Okay, now besides chemical reaction, we can also talk about changes in phases of matter. For example, from ice to water to vapor. So we can talk about each of these phases having different types of particles, and you can also consider this to be whether it's in equilibrium or not. Okay, so if all these three types of equilibrium are what you call satisfied or reached, okay, then we say that the whole system is now in thermodynamic equilibrium. Okay, so only in thermodynamic equilibrium that you can actually talk about well-defined pressure of the system, well-defined temperature of the system, and well-defined chemical potential. We'll talk more about this later on. Chemical potential is essentially relates to the types of particles that's involved. Okay, if it's not in equilibrium, then the properties of pressure can change, temperature can change, and chemical potential can change. Are there any questions at this stage? Maybe I should see you. Oh dear. Okay. Berpasan. Kejap I think saya pakai data saya sendiri. Okay. Just hang on. Okay. This is very bad. Even my recording has stopped. So let me just restart that. Are you seeing the screen now? Or hello, anyone? Sorry, I got my mic off. Are you seeing the screen now? Okay, I'm sorry about all these problems. Let me check. I'm trying to record. Okay, let me go back to my notes. Okay, I've actually come to already to this particular point, but I think probably I'll go back to this equilibrium thing. Did you get me speaking on this on equilibrium? Don't tell me I've already. Hello. Are you hearing me at all? Okay, sorry about this. Okay, I should I start at equilibrium then? Okay. Anyway, if you have any problems with respect to this, you can refer to the notes. So I was speaking about equilibrium. Okay. Essentially, there are three types that one has to be aware of. First is the thermal equilibrium, which sort of tells us how energy is dissipated between systems or flow of energy between systems. And then finally, this flow of energy balances out between the system and the net energy flow stops and the system is actually will be at the same temperature. So that's essentially what you often think about equilibrium per se usually, but it's really only a one type of particular equilibrium called the thermal equilibrium. We can also have the mechanical equilibrium where you can have the system, for example, the piston and the cylinder, for example. You can have things changes in temperature, then you find the piston moving up and things like that. So the system is actually doing work, okay, and then those mechanical work, okay, will need to stop at some point, and this particular when this particular thing happens, this is what we call a mechanical equilibrium. And then the other one is with respect to the contents of the particles of the system. So you can have flow of particles, you can have different particles inside the systems, and then they interact, and then they form a different species. For example, C and D forms a bound system, CD, for example. An example will be in a plasma, you have free electrons and free protons sort of moving around in the plasma, hydrogen atoms in that particular plasma system. Okay, so when the number of particles of such individual species have stopped changing, then we say that is a chemical equilibrium. Okay, and chemical equilibrium is not only for species of these different atoms or different molecules. We can have the same type of molecules but in different phases, like ice, water, and vapor, for example. So ice molecules and water molecules might be in equilibrium with each other, and then water molecules with vapor molecules can be in equilibrium with each other. Okay, so when they stop changing, when the number of what you call particles for each phase has stopped change, then we say that this is already in chemical equilibrium. Am I still there? Great. Okay, so I'm just worried. I think I better start using my data from now on. Okay, I can't rely on the faculty's Wi-Fi. So, okay. back to the notes. So when you have all the three equilibrium is satisfied, then we say that it's called a thermodynamic equilibrium. Okay, so in thermodynamic equilibrium, then you can have a well-defined pressure, okay, a well-defined temperature, and a well-defined chemical potential. Chemical potential is something to do with the species of particles in the system. We will look at it later on as well. So the final thing that I want to say today, I suppose, if I have time, is to talk about functions of states. Okay, then we have seen the idea of state coming from variables like pressure and volume before this. Okay, and then we can think of let me go back to that diagram earlier. Okay, we can think of changes within the isotherm going from, say, this particular point to this particular point. So I can do changes along this isotherm and then goes back up to the original configuration, original pressure or original volume. Then you find that one can do this irrespective of the process that one has. Okay, how should I say this? The idea is once you go to the final state, okay, going from one particular P and V, for example, to another particular P and V, all the things that what happens in between, are forgotten. So the only important thing now is actually coming from your well, I should not say that. One could arrive at, okay, I should go back to that picture just now. Let's draw it. I could arrive at different what you call different states of the equilibrium, okay, but how it arrives to a particular final point, okay, sometimes it doesn't remember what actually happens before that, okay, and usually this is what happens when you have a reversible process. We'll talk about that, I think, probably in the next lecture. But the idea is now, okay, whatever it is, we look at things with respect to the thermodynamic variables. In this particular case, it's your P and V. Okay. So as I said, you can define in an isotherm the temperature, and you have this function f as a function of P and V. So these P and V are what we call the state variables. And then your f is called the state function, okay, which defines the temperature. Okay, so the whole thing is now what we call the equation of state. So in this particular case, it's your equation of state for ideal gas, for example, is that. Okay, I think I've come to the end of the lecture now. So I will redo this again in the next lecture, for example, so that if you find any problems with this particular lecture, then at least you'll hear it again. Okay, I will be taking your attendance. So I hope no one left. Okay, here's attendance. Okay, that's done. So I hope to see you again. The next lecture is when? Wednesday, is it? Okay, so I'll see you on Wednesday, inshallah. Okay, everyone. Okay, bye.